I'm sending my greetings from Croatia today, and just visited the site of one of our solutions that we will present for the mortalities processing. Me and Christian has worked together, so we have one common presentation, and we will switch between each other as part of the presentation. Christian is representing Salten Havbrukspark, and I'm representing Wastewater, who are two participants in the GAIN project from Norway. As you may be acquainted with, the aquaculture industry has some side streams that are currently underutilized, and we have been focusing in the GAIN project to look at the more collection or capture of the side streams and how to bring them back into circular economy. And this three side streams we have focused mainly have been: one, the dissolved nutrients in the wastewater that you couldn't capture as particles. You have the particles, which consist of excess feed and feces from fish. Then you have the mortalities or discarded fish from the breeding cycles. This is a picture of the state of the Norwegian aquaculture industry, which is the world's largest on salmon and trout, and to show you a little bit about the mass balance and the size of the numbers we're talking about. As you can see, we use more than 1.6 million tons of fish feed for the aquaculture industry in Norway, and we get more than 1.25 million tons of product to the market. However, the biomass lost in between is coming out of this process as a side stream, either as a sludge from feed and feces, or mortalities, or dissolved nutrients mainly. So the aim in our part of GAIN has been to transform these side streams into new raw materials suitable for other industries or potentially back to the aquaculture industry. As a background for our work, we mapped available technologies to capture the nutrients from the aquaculture industry, and we looked at the different technologies and how well they were performing at the beginning of the GAIN project on fish sludge. The capture of fish sludge was not done previously in Norwegian aquaculture. Usually you could release the sludge into a water body like the ocean or to some freshwater recipient that were able to receive that kind of nutrients. But then the Norwegian government started to set some measures that they are not allowed to increase capacity or build new sites if they are not collecting a certain amount of the suspended solids and reduce the chemical or biological oxygen demand. So in the mapping, we looked at different technologies, and we included in this slide just a few of them, which are the typical, some of the typical ways of capturing it. If you work in the aquaculture industry or are acquainted to that, you would probably know drum filters, which are typically used to clean as the first step. In the flow-through or RAS facility, you capture particles from a large amount of wastewater by using a drum filter from Hydrotech or some other solution provider. this will deliver a kind of thickened wastewater. I still call it wastewater and not sludge, since it's very low in dry matter. We have seen typically from less than 0.1% to maybe up to 2 or 3% maximum as the output of drum filters, depending on how they are being backflushed and the size of the mesh used in each of the drum filters. But this is still a lot of water and very little organic material in it, so you need to have some additional steps for reducing the amount of water in the sludge. One solution can be a settling tank with lamellar or other technologies, with or without any additives or polymers. This typically brings the dry matter up to about 3%, 2 to 5% more or less. But still you have a lot of water present. We evaluated also the magnetic particle separation technology with a company called Mivanur, and we found that was able to increase the dry matter to somewhere between 20 and 50% dry matter, but then you add some magnetite product, which had some impact on the end product and the applicability of the end product in other industries. I'll come back to the applications of the dewater and dried sludge in a minute. Then we looked at the S3 filter system, which Christian will present in more detail. That was a very promising technology for taking a thin sludge received from the drum filters and getting it quite high in dry matter. At the beginning of the project, we were not certain about how high in dry matter we were able to have this sludge, but Christian can tell you now more about the results from that part. Typically, in many applications, we see rotating band filters from different suppliers. They would need to have an input maybe 0.1% or in that range, and can deliver up to somewhere between 10 and 30% dry matter is typical for a band filter. With good operations and good maintenance and good cleaning of the systems, you might get above 30 on some of them. But usually you end up somewhere between 13 and 22% on most band filters. So that can be an intermediate step, but still you don't get the really dry product out of it. Then we have screw presses, which come in different varieties as well. Screw presses have a reject wastewater, which can be put back to the previous step if you, for instance, combine it with a rotating band filter. And then you can have up to 30 to 35% dry matter from a screw press if it works well. But again, like with the band filters, it's crucial that you have good cleaning, good maintenance, and the right design of the screw press. And then we in Wastewater have worked with drying technology and have developed a well-functioning drying technology based upon the experience in the GAIN project, which I will also come back to in a minute. So we chose two of these technologies that seem to be the most promising ones that could enhance the use or dewatering and drying and then use of the wet food feed, the wet sludge to become a new circular economy product. And that was the S3 filter system, and it was the Wastewater superheated steam dryer. When we did this choice, we were looking at trying to have a simple system with as few steps as possible from the primary filtration from the drum filters to an end product that is dried and stabilized and easy to transport and easy to store until you can use it in a new application. And also we wanted to have a robustness in the process. So if one technology leaves at a certain dry matter level, the other one will pick up this product, even if the performance of the previous process is not optimized completely. So you have some overlap in where one technology leaves the product and the other can start the processing. And of course, we also wanted to have the highest quality of the dried end product with the best properties of the product. For the sludge itself, you will get some more details, but the main legislation in Norway on fish sludge is that you need to remove between 50 and 70% of the particles above 0.45 micrometers of size. And at the same time, you must comply with the requirements of minimum 20% reduction in chemical or oxygen, biological oxygen demand. The sludge is typically very low in dry matter when it's collected by the drum filters in the primary filtration. And as you can see, the nitrogen and phosphorus level are quite high in the wastewater. So those are the most important nutrients to actually capture and try to utilize. We also chose to limit the focus to freshwater fish farming and land-based aqua farms with less salt in the processing water. You have some smoltification in the end of the hatchery breeding cycle, which means you have about 1 promille of salinity in the wastewater that we treated. So I'll leave to you to continue now, Christian. So the word is yours. You have to turn off your mute.
Thank you. Thank you, Heistein. So to continue, I will first characterize the wastewater from smolt production in detail. And so if you look at the uppermost part in the table, you see something here that is called suspended solids. And this means this is the particles, so the organic particulated matter that we find in the wastewater. And you see it's 0.006 to 0.18%. So this means the concentration of particles in this types of wastewater is very, very low. If you take this wastewater, put it in a glass, it looks like tap water. So you have the impression you can drink it. If you smell it, it has no smell, nothing. So however, it contains these particles and we must remove it. And this poses a really high challenge compared to other types of wastewater. So the particle diameter is usually very small. It's several micrometers. It doesn't reach the millimeter size usually. Further, it consists of organics. So this is something that you see by the biochemical and the chemical oxygen demand. And of course, it contains also a lot of different ions. Some of them that are interesting from a commercial perspective is, of course, nitrogen and phosphate. So nitrogen is present mainly as ammonium, and phosphate mainly as orthophosphate. And especially orthophosphate is important, potential important product, since in future we expect that, as Roberto already mentioned, that phosphate is limiting, and of course it's a great value that we dump in the sea every year by just leading the wastewater into the sea. In addition, phosphate and nitrogen cause a kind of eutrophication, and in Norway the marine environment is pretty sheltered. So we have a lot of bays and fjords where the water body is not exchanged frequently, and therefore, if deposed in the wrong environments, these nutrients cause some eutrophication. Could you go please to the next slide? Thanks. So the technologies to remove this dissolved substances are classically based on usual filtration, as we know it from municipal wastewater cleaning and so on. However, this is not sufficient, since the particles in the wastewater are so low in concentration. So therefore, these technologies require so far either a supplement with coagulants, or they must be treated with something that is called sonoelectroflocculation to precipitate this dissolved nutrients, or very low concentrated nutrients. And another possibility that we have investigated is to remove nitrogen and phosphorus by cultivating seaweeds in these wastewater, so by aquaponics. Could you please go to the next slide? Yes. So what you see here is a typical magnetic particle separation device. So this works in a way that before the wastewater enters the device, it is mixed with coagulants. These are usually polymers that have different partial charges. And these polymers, they attach to the nutrients that are dissolved, or also to the smaller particles that are very small, and make them to form larger aggregates. And very quickly, these aggregates build up to particles that are larger than 1 millimeter. So you can see them by your eye, and then they can be removed. And this technology removes phosphorus very, very efficient. So we have almost 100% phosphorus removal. However, nitrogen doesn't react so well with this technology, so there's a 30% removal. But on other suspended solids, some organic solids, fats, and so on, also remove very well. So this is a technology that is very promising. Could you go to the next slide, please? Another technology to remove dissolved matter and very small particles is called sonoelectroflocculation. Here you see the device, and also here the wastewater enters the device, and in the device it is exposed to a very strong electrical field, and additional is treated by ultrasound waves, and the combination of this ultrasound and the electrical field also causes the particles to participate there and to form larger aggregates. This is very efficient in phosphorus, nitrogen, and suspended solids removal, so very, very efficient. For both devices, it was planned that we would test them in GAIN. However, we could not do this, unfortunately, due to this COVID situation, where people from different countries, experts from different countries, could not travel to Norway to install these devices here. So instead, could you go to the next slide, please? Instead, we have tried aquaponics with seaweeds to remove dissolved matter. So for seaweed aquaponics, we used small, fast-growing seaweeds like a red algae and green algae. So they were well suited for aquaponics. We have tested them in pre-trials in such basins here with defined nitrogen and phosphorus concentrations. And we have tested more than 10, maybe 20 different species, and found that Ulva lactuca, the sea lettuce, was best suited as a production crop in such aquaponic systems. So the juveniles and the seedlings are easy to produce, and it grows very quickly, and so it more than doubles the biomass every day if we grow it outside. And To grow this, we had to use a mixture of wastewater, which is basically fresh water, and seawater. Ulva lactuca is also growing very well in brackish water conditions, and therefore also this supported the choice of Ulva as a production crop. And we grew the seaweeds in 4 square meter tanks that were covered with approximately 20 centimeters of water. And then we measured the weight as a result of the seaweed. So we found that a permanent production where you keep a certain level of the algae in the tank, and then you harvest approximately 50%, and keep the rest to grow out again, were performed best. And so we did this in a pilot scale, you can say, and then we stipulated the results to a full production site of 15 hectare, including 10 hectare production area, and we tested this also in the natural light conditions in Norway. So to produce such a crop, it makes not much sense to produce it with artificial lights, since this costs a lot of energy. And so we used the natural light conditions here, and therefore there we reached. Let's have a closer look here. So we reached a productivity of 0.4 tons dry weight per day in this 10 hectare farms. And we anticipated that we have only a 4 months productivity of 30% and 2 months unproductive, whereas the rest of the year is fully productive. And therefore estimated yearly productivity for 85 to 90 tons dry weight. This would correspond to a yearly nitrogen uptake from approximately 3 tons, and a phosphorus uptake of approximately 0.2 tons. And if we compare this to the waste characteristic of the wastewater of Helgeland Smolt, which is a salmon producer, a local salmon producer here, then we can say we can neutralize between 40 and 70% of the nitrogen that they produce, and also between 3 and 6% of the phosphorus. So the ideal solution would be to combine one of these technologies that are effective on phosphorus, for example, sono electroflocculation, with this nitrogen removal by aquaponics. I must also say, however, these aquaponics are so far only in a pilot scale, and it needs some more effort to scale this up to an industrial scale. Next slide, please. So what are the aquaculture regulations in Europe for the emissions? So we have also investigated this and found very quickly that aquaculture emissions are regulated very differently in Europe. Not only on a country level, but even on a local or municipality level. In Denmark, for example, the land-based fish production requires a permit for discharging water into the sea. And this permit is quite individual. So the authorities, they look at the place where the farm shall be installed. They look at what type of feed is used, and what water source is used, and so on. And however, in general, we can say there is a certain demand for purifying this water usually, and especially if you build a new farm, you will be obliged to purify the water. There's a certain restriction to the maximum feed allowed per year, and to the maximum content of nitrogen and phosphorus. Such type of rules you find almost all over Europe. And then I will take Norway as a specific example. So in Norway, the rules are regional, and so you need to contact the regional authorities if you want to do aquaculture, and to ask specifically what type of rules they have. And usually you need to define the tonnage of fish that you aim to produce yearly. And then you need to establish a production plan, including the feed use for this production. And the feed needs to be specified, so its chemical content needs to be specified. And from that chemical content, the producers need to calculate the respective emissions and send this to the authorities. And these emissions need to be monitored regularly, and it may be also checked by the authorities. So they may come from time to time and take samples themselves. And usually the removal of particulate matter is not mandatory, but in all new farms that are established is mandatory. And basically, in most municipalities here in Norway, you need to remove particles that are larger than 0.5 micrometer and at least 50% of this particles. And you also need to reduce the organic content measured as biological or chemical oxygen demand, also by at least 20%. And most to reach this goal, most farmers use recirculating aquaculture systems, since the water can be recycled permanently there, and therefore much less filtration and purification effort is needed. Next slide, please. So here you see a typical particle profile from the aquaculture wastewater. This aquaculture wastewater is already enriched by a drum filter, and this is a large particle that you see here on the picture. So, but you see most particles are smaller than 50 micrometers. So next slide, please. So the particulate matter in the wastewater is very dry, so it's usually below 0.02%. And as I said, this poses the challenge to purify these waters. And the existing technologies are based usually on the technologies that Halston has presented already. For example, drum filters with 20 to 80 micrometer. They are used also for initial dewatering and concentration of particulate matter. And then it's followed usually by filtration with coagulants, polymers, or magnetic particles. And however, in Gain, we developed a filter dryer together with a Swedish company, LS Optics. And we identified this as a very promising technology, since they have a very fine filter using a mesh with a size of only 6 micrometer, which is much lower than this 20 to 80 micrometer. And however, during the GAIN project, we could develop this S3 unit towards an efficiency to purify more than 90%, 80–90% of the particles, to remove 80–90% of the particles from this wastewater, and to receive a dry matter content of more than 90%. Next slide, please. Here you see the S3 filter in an overview. So if you look at the top figure, then you see basically here the filter drum in white, and below the filter drum you see the buffer tank. And the filter drum is rotating in the filter in the buffer tank. The buffer tank contains the wastewater. It's already enriched wastewater that is concentrated by a 80 micrometer drum filter. And on the left side, you see a so-called vacuum tank. And this vacuum tank is connected to the drum filter and sets the whole drum filter in a vacuum. So there's under pressure, there's a lower pressure in the drum filter, and therefore the water and the particles is sucked on the filter surface. The water penetrates the filter and is going to the waste stream there, whereas the particles stick on the outside on the filter. Then, as you see, only 20–25% of the filter surface are sticking in the buffer tank. Then the filter, while rotating, is going out of the buffer tank, and there the particles start to dry and form a kind of sludge. And this drying is mainly performed by the vacuum, and it is, we installed infrared units above the filter, providing the filter with some extra heat. And this supports the drying process so that we have finally, when the filter drum reaches the other side, that we have finally a sludge product that contains almost no water. So we reach a dry matter content of more than 90%. And from there, the sludge is scraped off automatically by a knife and then transported to a big bag filling station by a band. And yeah, I can go much more in detail here. And so if you're interested in further details, please contact me directly. I think since we are quite limited in time, I will not go much more in detail here. I may just say the system runs fully automated, so everything is automated as far as possibly. Everything is controlled by sensors, all the water levels, sludge levels, and so on, and vacuum. So this is fully automated and means almost no maintenance. So next slide, please. Yes, so here you find the description of the whole process that I explained just now in detail. So if you're interested in a more detailed explanation, I would ask you to read through this. So here you have a summary. You have a summary of all the results that we achieved with this new S3 filter. So you see all the chemical details. You see the wastewater here on the left side, chemical characteristics of the wastewater. Here, chemical characteristics of the sludge after purification. And that's what we call condense here is the wastewater. So basically all the water that goes through the filter evaporates, and therefore it's very, very pure. And so also this is something you should have a look in detail. So it's, I guess, too much to explain all the details here. Could you go please to the next slide? Here you see the S3 filter in an overview. So you see the filter cloth is sticking on a kind of metal mesh. And the filter cloth has a very, very fine mesh and needs to be exchanged once a year. And yeah, could you go to the next slide, please?
Yeah.
Yes, and this would be then again Heistein's part. So if you have further questions on the filter dryer or the aquaponics, please contact me or ask them in the chat afterwards. Thank you very much.
Thank you, Christian. Now you've seen the S3 system and the explanation about that part of the project. In Wastewater, we were looking at drying technology or using superheated steam as a drying media, and with mechanical fluidization of the sludge inside the drying chamber, and finding a way that we don't get lumps and clogging inside the drying chamber when we dry this sludge. We know a lot of conventional drying technologies have problems with lumps building up and the product sticking to all surfaces inside. So we had a way of using a bed of dried product inside the dryer as a starting base, and then add small portions of the wet sludge into that base of dried product, fluidizing it, making a very large surface to interact with the superheated steam, which makes a very efficient drying process. And this has been tested and further developed and standardized through the GAIN project. Here you see a presentation what it looks like on the inside of one of our dryers. And if you look at the lower side, you see a pipe coming into the drying chamber. And on the picture on the lower right side, you see a typical setup with a small buffer tank with an agitator inside to keep the wet sludge homogeneous, and with a sludge pump feeding through this pipe into the drying chamber. Then we discharge the completely dried product, which is well above 90% dry matter. Typically, it ends up like 94 to 97% dry matter, more or less, in big bags, which is then in the process microgranulating and forms powder that doesn't make a lot of small particles to make dust in the atmosphere, and it has very low odor. So it's quite a pleasant product to store and to transport, and with a bulk weight of typically 750 to 900 kilograms per cubic meter, it's also economically viable to do transport and distribution of that product, compared to some other technologies doing a kind of drying process to the sludge, which then becomes more porous. The input of our system, as you saw in the previous slide, needs to be somewhere between 10% dry matter and up to maybe 35. We use low temperatures inside the dryers. We have, in the GAIN project, reduced the inlet steam temperature from close to 200 degrees to about 140 degrees that we use today. And this also means that we contain more of the nitrogen content in the dried product than we did previously. And since we use superheated steam as a drying media, you have very low levels of oxidization, since there is almost no oxygen present in the loop inside the dryer with the drying media. On the upper right side, you can see a typical processing of fish sludge, where you, at the bottom of each of these cycles, you see the blue curve or relative humidity inside the loop of the dryer. It's very low, and then it goes up to the maximum level allowed through the first feeds into the drying chamber or the wet sludge, and then it feeds until it accumulates enough product to have a final drying stage, and then discharge a portion of the product inside. Somewhere 60 to 80% of the product is discharged, and the rest is the base for the next drying cycle. One of these drying cycles is typically 1.5 hours. So this is a semi-continuous process, and it's all fully automatic. So as long as you have sludge available, the machine will go to a new drying cycle. I'll not go into details to explain how the machine works in this presentation, and I can do some more details if you are interested in that later. I will then have a look at what can this fish sludge, when it's dried, become as an end product, and what kind of value do we have on these kind of end products. And we investigated a number of applications in the GAIN project. One of them was for the insect feed. As you see on the left side, black soldier fly larvae was fed with aquaculture sludge. The larvae really enjoyed the feed they were given, but there is some issues regarding the regulations in the EU on the legal side. We had some news that this might now be legal, so there is some change going on currently. So maybe this will actually be a potential way of valorization of the sludge in not far future. So it has a potential value as an insect feed. What we know for certain is that the dried product has been used as a very potent biofertilizer product because it's rich in nitrogen and phosphorus. And we'll also comment on the levels of zinc and potassium in a coming slide. But it has a certain value. in the European market, typically, if you look at these nutrients, the value used as a fertilizer by the farmer will be from 250 euros per ton and up to 400 euros per ton. But it all depends on the distribution channel, the packaging, how many intermediate steps of processing you would add to this raw material. If you want to have a full fertilizer value, you would need to add some potassium component and maybe some other minerals as well. And that means some processing costs. So yeah, typically today the fish sludge is collected free of charge for the fish farm or at a very low value or low cost at the fish farms when it's dried. It has a high cost if it's a wet sludge being collected. So biofertilizer seems currently to be the best valorization, as long as you can't use it as an insect feed or have some other applications that have a higher value. You can also use this as a biogas substrate or by direct incineration as a bioenergy product. There have been a lot of initiatives to try to use the wet sludge or dried sludge as biogas substrate as a single substrate. These have not been very successful, and that's because the ratio between nitrogen and carbon inside the bioreactors have been not the right conditions for the bacteria that is doing the digestion process. So the nitrogen level is too high compared to the carbon. So you need a carbon-rich substrate to mix it with to have a balanced process over time. That's the main feedback we have from those who have tested the biogas process on fish sludge. The cement industry is interested in replacing fossil fuels like black coal, and they have tested incinerating this as part of the production process of cement, and they are very happy about the dry matter and the energy content, but the willingness to pay a high price for the product is not presently there. So we're talking about very low value of the product, and of course transport cost is a discussion between the buyer and the seller in these applications. In Norway, you also have quite a lot of transport distance between the fish farms and the industrial plants that can use this, and also the larger commercial biogas plants. We also tested on pyrolysis of the dried fish sludge to convert it into biochar. This proved to work well in the process. Of course, then you reduce the weight of the product even more. If you mix the biochar with organic compost, it might be a very good fertilizer product for agriculture. But there is some cost related to the pyrolysis process, and the amounts of each aquaculture plant doesn't defend the investment cost. So typically, if we look at the dried fish sludge, it contains 93 to 96% or 97% even sometimes dry matter. So, and it's not hygroscopical, so it doesn't add moisture when it's stored. We have had some bags of this product stored outdoors during the Norwegian winter in the northern parts of Norway, and we collected some samples this summer, and still it didn't attract substantial amounts of moisture, so it was still above 90% dry matter and no biological activity in it. Energy content is about 20 megajoules per kilogram, and fat content about 3.5%. So as I already said, using it as a biofertilizer product, that seems to be the best valorization currently. And this is based on the Norwegian legislation for biofertilizers. You can spread up to 4,000 kilograms per acre in a period of 10 years with this product as it is. Since it's a quality class 1 fertilizer. In Norway, we have 4 quality classes. 0 is the best, 1 is second best, and then you have 2 and 3. With the increasing class, we have less amount allowed to be spread per acre, and also limitations on what kind of plants or applications you can have. So a category 3 fertilizer is not a very good fertilizer. You can use it for like your lawns or grasslands that you don't use for feed for any animals and so on. But the fertilizer in quality class 1 can be applied to food production, and it's with the only limitation is the amount per acre. The latest test we have also on the content is that the nitrogen level is about 7%, which means we have a very low loss of nitrogen in the drying process. Phosphorus is 3.4%, so there is obviously some loss in phosphorus compared to the wet sludge or the wastewater. Potassium is very low, since there is very low levels of potassium in the fish sludge in the beginning. We had some studies from NIBIO, Norwegian Institute of Bioeconomy Research, showing that this is a very potent biofertilizer for barley and other grains. The company A, C, and D here are other dried fish sludges, and the waster one you see is the highest column, which had the best yield on the growth of the plants, even better than the mineral fertilizer. These were all having the same nitrogen level, so the level of potassium and other substances were varying, but it was the same nitrogen level in all fertilizers. The growth curve for the plants using several of the other fertilizers were they were releasing the nutrients very much in the beginning, and then the growth was leveling out, while on the dried fish sludge using the wasted drying technology, it has a very steady growth curve through the whole cycle of the barley, which means it released nutrients gradually through the cycle of the crops. And this is because of the microgranulation. This releases the nutrients slowly to the plants. So in the end, the growth was better, and the plants were more resilient to weather and wind. Yeah. The only component in the fish sludge that makes it a quality class 1 fertilizer and not a 0 in our analysis is the zinc component. And the zinc component is from the fish feed, which contains a certain amount of zinc for the gut health of the fish. Since this is mainly mineral phosphorus, which is not very bioavailable for the fish, it means most of it, I've heard numbers of approximately 95% of it is not collected by the fish, but then remains in the feces of the fish. So that explains why it's high in zinc. Different areas with different soil has low or high levels of zinc, and in some areas in Norway they actually add zinc with a fertilizer because they need to increase the zinc level. Some other places have surplus of zinc in the soil and doesn't need that component. So this is very much a question of the need of the local soil, if this is the best fertilizer or not for the plants. As last part of our presentation, in the game project, we also looked at the third side stream, which was the mortalities and also discarded fish. This was first done by us on a smolt farm, Helgeland Smolt in northern Norway. There is always some loss during the breeding cycle, both in the hatcheries and also at sea sites. What is the most commonly used process today is the ensilage, which means you need to have formic acid. You mix that with the fish, and also you usually add some water in that process with the grinding and mixing with the acid. This has, however, some side effects, and that's some injuries and work-related hazards with the treatment of the acid locally and also during transport and storage. Even deaths have been as a consequence of some of the incidents, and many serious incidents and many minor where they have breathed the gases from the ensilage tanks or get a skin burn from the acid. So we looked at the way of processing the mortalities by drying it locally instead of using the formic acid. And we have made also analysis of the bacteria content of Enterobacteriaceae and sulfite-reducing bacteria and salmonella on the samples. And in none of the samples we had a level which was measurable of these bacteria. We had one sample that had some bacteria, but we did the new test on that sample and found out that there was some contamination of the first sample that we analyzed. So it was not the correct result. So that means it's a totally safe product to store and to transport, which is very important because you don't want to have any contamination or diseases from one fish farm to any other fish farm or any part of the logistic chain. The application of this product, we have looked at the number of different ways of applying it. Pet food is a very interesting potential high value. We have been discussing a lot about how this can be seen as a category 2 or category 3 product in the EU and EES legislation. We have for now considered it being a category 2 product, and that means we can't use it as a pet food ingredient directly without clearing this with the legislation. But if the legislation opens up to use it, it can be used as dog feed or cat feed as part of these feed fractions. That would be a very good application. It can be used as a biofertilizer product. Of course, it's food safety again, and you really need to prove that this is free of the bacteria, any contamination that can goes into a local stream and send some disease to local fish. So you need to be very aware of food safety. What is done today with the ensilage is that it's typically delivered to biogas plants. So we think the best value today is also to take the dried product to a biogas production plant, because they already received this product, and we reduce the transport and weight and volume by 80 to 90%. So it's a substantial reduction in cost. Of course, it can also be incinerated in industrial processes like cement factories, but they need to have some amounts of it. So we're not there yet, since each site produces small amounts of this product. Technical applications is also a term which is typically focused on the oil component, but we have dried this with the oil component inside. Fur animals like fox or mink can be bred with this today. Zoo and circus animals and other non-food producing animals can have it, but that's limited markets, so that's why. Yeah, final remark on this process is that fat fish like salmon or trout seem to be more difficult to dry than, for instance, sturgeon, which has less fat in it. So to overcome this issue, we needed to find a additive, and we tried two additives. One is the wood chips, which has currently been used on both a hatchery and also on a trout farm here in Croatia, where I'm currently. And we have also in Croatia tested with dried spent grain. And if you are going to use this as a pet food, dried spent grain can be an ingredient, but not the wood chips. Wood chips can be for biofertilizer or bioenergy product. So that's my final remarks, and I say thank you very much for attending. Have any questions, you can contact Christian or me at those email addresses. Thank you.